Albany ID? Because I think if you sign in through an account other than, like, if you don't let it route you to your UAlbany sign in, then it's not sure, it's not as confident about who you are. And so it'll, I don't know, it may delay you or something. All right, we're still missing about 70 people. So I'm not sure what's going on. Maybe we'll wait a couple minutes. All right, right. Yeah, how many of you lost, here, actually, here's a, do this by poll. The meeting was for 2:12. How many people lost power at some point over the last 24 hours? Just curious. All right, so fair number. Wow, it's all right, so it's a lot. It's 65 no so far, 13, 14 yes. All right, so let's just, in case people are having trouble, let's wait a minute or so. This is not a good class to miss because Gauss's law is tricky. So the meeting was for 2:12. Huh. Yeah, I don't know what Zoom is doing. All right.
Hello, can you hear me?
Yeah, I can hear you.
Do I even have my camera? Hello, I have a camera.
All right, someone with the camera. The rest of you can turn your cameras on too. It's not forbidden.
Even though I'm look like a bit of a mess, I apologize.
Well, no, that's all right. It's only sometimes when I actually join a class and see, I was like, oh shoot, I didn't shave. So it's
yeah, the mask also doesn't help with that. You're like, oh, I have a beard.
It's a
I
plus.
know, I have that problem too. It sucks.
Yeah.
Yeah. Professor, just a moment ago, you were talking something about Zoom. I couldn't hear you. I was still setting up everything. What was going on?
Nothing really. It's just Zoom is being a little flaky. And we're down right now. We're down about 50 people.
Yeah. Well, considering that I went outside about 15 minutes ago and the entire world is encased in ice, as in, hold on, I took pictures. The pine trees are literally like ice. And the regular trees too.
Yeah, I know some people lost power, so there
like,
may. Wow.
Like encased in ice, literally frozen over. And I know that doesn't help some power lines.
Yeah, I think the weight is bad for them. Yeah, so the I'll send out an announcement about this, Eric. But you're yeah, no, there's no quiz corrections or anything, but the lowest quiz will be dropped because everybody can run into some sort of catastrophe. Their alarm didn't ring or their something else goes wrong. So yeah, so lectures are not recorded, but I'm going to start posting more example videos sort of to supplement, just to supplement the lectures. The quizzes, you take the quizzes are in recitation section. And
we do have discussion once a week.
Yep, discussion once a week. Yep, they're starting, the quizzes started yesterday.
Yeah, so I've been attending discussion for the last 3 weeks. I've been I heard you mention some other things about going to discussion more often, or you might have been talking about office hours.
You can. So this is the thing about through the miracle of Zoom, there's no room capacity doesn't matter.
If you want another example, you can just go to another discussion.
Yeah, and in fact, I know last year during this class, during COVID, so you have to go to your own section to take the quiz. Yes. And the quizzes are different between different sections. So go to your own.
I had Professor Lanford last semester. He was the same way.
Yeah, but in terms of discussion, if you have more questions or you just want to see the other TA work through the examples, then just go to another discussion section. You can go to all 6 or 8 of them if you want. And, there were last semester, there were a few people who would go to 2 or 3 of them. So yeah, look at, as far as scheduling details, just look on the day-by-day syllabus, right? So this week, there is the first quiz, right? Okay, so, oh yeah, and there is one poll here. So first, there are no office hours at all today. I have meetings I can't move, and so I can reschedule with people if you need more help after recitation section. And the other question is, I was thinking about, because in one of my other classes too, there's an issue of, some people really feel that in-person office hours are helpful. And I know some people, obviously I'm not going to, sorry, I'm working on Zoom at the same time. Zoom office hours will still happen because I know many people are remote and have to be remote. But
Like
if I had an occasional in-person, don't answer this yet, you don't know the question. If I had an occasional, like on campus in a large classroom office hours, would you show up? Like, I don't want to do it if nobody would. So answer the poll and tell me whether you, like, I understand no could mean no, it'd be completely useless, or no, I live in New York City and I can't drive to Albany for an office hour. But if I
for
had
example,
would you
I'm going to say
sometimes
no because I can't go on campus because I'm fully remote and I decided not to do all the testing stuff.
Right.
Because
So,
I didn't need to.
yeah, if you are able to go to campus logistically, would you show up for an occasional? It wouldn't be that often, but just sometimes. I think it's a little more productive to be in the same room. So if you
Personally,
can, I would do it. So click yes if you would/could. No if you can't or don't want to. And I'm not sure about the people who are saying greater than, less than, or equal. You may want to reconsider that answer. Okay. All right. So there's somewhere, take a few more seconds, but then we got to move on. All right. So there's somewhere in the order of 40 to 50, 40 odd people who would. Okay. All right. Yeah, greater than. All right. So let's see where we left off. We were talking about Gauss's law, and Gauss's law is tricky. Once you see it, once it hits you, it'll kind of make sense and is very nice. But until that point, it's one of the more subtle things that we do. Right. So Gauss's law tells us that the integral over a closed surface of E vector dot dA vector is equal to Q enclosed over epsilon naught. So, and it's very important to understand how to use this. You cannot think of this as just some crazy formula with a bunch of symbols. You have to make each of these mean something physically, or it's almost impossible to make sense of it. So this left side, this is used so much, there's just another variable we use for, a name we use for that, phi sub E, or electric flux. Right? So that's not like some equation or something, it's just that you write this thing all the time, and so you just give a label for it. So this quantity is known as electric flux. And we talked about last time what that quantity means. It's basically the electric field flow through some closed boundary. So you imagine this thing is it's not a line, it's a closed surface. So some sort of screen, like a ball that made out of screen that's kind of been squashed a bit, or a potato, you can think of it as a potato skin. The electric flux through this closed surface is basically all the electric field lines going through, the amount of electric field times the surface area summed over the whole surface. And it's easier to picture with water. So if I had an object here spraying out 1 gallon per second, then the water flux through this wall, the total water flux through all parts of the wall would be 1 gallon per second. And if I said, I want you to prove that, you would have to go through and you'd have to find for each little square of this screen, you'd find how many gallons per second per meter squared there are here. But they're not flowing straight out through the screen hole. In some cases, the screen hole is facing this way and the water's going that way. So it may be a gallon per second that would flow through the screen square if it were facing the flow, but it's tilted, and so it's less. And so you can see why this thing winds up being an integral, because you have to calculate the flux through each little part of this whole surface, the parts coming toward you here, the parts going away from you on the back. And it's the flux is the total of all of those. And you can also then see if this thing were spraying out 1 gallon per second, the total flux through this curved surface would be exactly the same as the total flux through this curved surface. It really doesn't matter. If this is sending out a gallon per second, I know that a gallon per second, one way or another, is coming over through all the square screen holes of this blue surface. And I know it's also true for the red surface. So this is the key point of Gauss's law. You know, there is an integral where you know the answer. You know the answer to the integral. I don't know what the flux through this weird shape is, if that's spraying a gallon per second. I don't know the flux through that square or this one or this one. But I do know the integral of flux dotted with surface area integrated over the whole closed surface. It's got to be a gallon per second. And that's what Gauss's law tells you. Gauss's law tells you the electric flux through any closed surface is equal to the charge inside it times this constant. Right? So if I have a charge here plus Q, and I have a closed surface here, and again, this is a 3D surface, not a line. So I'm just, it's all you can see of it, but it's a potato skin, not a line. Gauss's law tells me that if I found, right, I know at this spot, E points this way, and dA points, I guess, that way. So dA points normal to the surface, E points away from the charge. So here's dA vector. dA vector means a vector whose size is equal to a little piece of area and whose direction is straight out from the surface. And there's the E field here. And then at other spots like here, E would point this way. dA vector points that way because dA points straight out. E points away from the charge. So E dot dA, I could find the flux through a little screen square right here. And, the E field's not aimed straight at the screen square, so I would have E, the flux through this square would be E, the strength of the E field here, times dA, the size of this square, times cosine of this angle. And if I wanted the flux through the whole screen boundary, I would have to compute this integral over the whole closed surface. And so you'd need to know what the exact mathematical shape of that surface was. But this is the miracle of Gauss's law, is that you know what the answer to this integral would be. If you actually did this integral, you would get that it's equal to the total charge inside the closed surface divided by epsilon naught. So if you did this whole integral, if you integrated E dot dA over this whole closed surface, I guarantee you would get Q over epsilon naught, because Q is the amount of charge inside it. Now, you could also say, you could take this case, I could take a charge plus Q and a charge minus Q. And I could say, what's the integral of E dot dA over this whole surface? It's going to be a pain, right? Because here, the electric field at this point, let's say here, the electric field at this point from this charge points that way. The electric field at this point from this charge points this way. I don't know. I guess this one's longer because it's closer. And then the sum of those two vectors points, kind of this way. So E at this spot might kind of point, right? I got to add this vector and that vector and wind up with something, I don't know, kind of like this, I guess. So that might be total E. And dA will point out. So good. So I'd have to evaluate E times dA times cosine of the angle between that and that at this point. And then I'd have to do it for every point on that whole surface. And at the end, what would I get? What's the integral of E? You don't know what E is at any of these spots because you don't even know the shape of this surface, but you do know what this full integral is. What's the value of this integral, E dot dA integrated over the whole closed surface? And then Jade, I'll answer your question in just a second. If I forget, you got to unmute and remind me I forgot. But somebody tell me, what's this integral? If you could do the whole integral.
It's going to be
yep. Good. A couple of people. Yeah, it's 0 over epsilon naught. So it's 0. Because, right, epsilon naught's just a number. So this whole integral, if you could do it out, I already know the answer to the integral. All right?
Professor,
so the answer to the integral is 0 because the total charge enclosed by this surface is 0. So, okay, go ahead. Somebody was, oh wait, first Jade asked a question. Why is E and dA pointing in different directions? Right. So if you're here, the electric field is the mix of these two blue vectors. So E points that way. So E points in the direction of the total electric field from all the charges. And dA points straight out from the surface. This is not a phi. That's an integral. Trevor? Yeah, so. Okay, so at first you might say, wow, that's crazy. I don't even see how why would that work out to be 0? Go back to the water example. Suppose I have something that's spraying out 1 gallon per second, and I have something that is pulling in 1 gallon per second here. So I have some machine that sucks in 1 gallon per second into that spot and somehow stores it. Let's not worry. I know water isn't compressible, but let's not worry about that for now. So this is pulling in 1 gallon per second. That's spraying out 1 gallon per second. And I do this, and here's my screen blob surrounding this, and I dunk this whole thing in a river. And the river's flowing this way. What's the total flux through this whole wall? Nothing. Because this has a net, if it were just this, there'd be a net, if this is spraying out 1 gallon per second, there must be 1 gallon per second flux outward through the wall. But if this were the only thing, there must be 1 gallon per second coming in. Let's suppose it's just suppose it's a lake, not a river. So let's not worry about another current flow. So this whole thing is dunked into a lake. This thing is pulling in 1 gallon per second. This is pushing out 1 gallon per second in different directions. I know that the net flow through the walls must be 0 because the total inside isn't changing, right? Because this is a net gallon per second leaving and a net gallon per second coming in. And so the total is 0. So I may not know what the flow is through any one spot on this surface, but I do know the total. All right. Yeah. So why would we ever need to take the integral? Evan, we will. We're going to do an example, right? So it's not always quite this trivial. I'm just showing you the basics of how to get started. Right. Do we assume it's never full? Yeah, so don't worry about like full. So if I had, you imagine this green potato skin, I dunk it in a lake, the net inward flow and outward flow is 0 because it's just all the water is still. But now if I have something in the middle of it that's pushing out 1 gallon per second, that has to be the net outward flow through all the walls, through all parts of the wall, if you summed it up. Okay.
Excuse me, sir. What's that symbol integral with a circle?
This integral with this, so it's just an integral, but the circle is to remind you that it's a closed surface.
Okay, just a reminder, right?
Yep. Yeah, I mean, it's done the same way. It's not a different technique.
Thank you, sir.
Let's see. Yang, you have your hand up, or somebody has.
Yeah, I'm young and I finished.
Oh, okay. Okay, good.
I have a quick question too. So whenever like there are opposite charges inside and they have like, for example, both of them are 1, so it will be always 0 when they're equal but opposite.
Yep.
Okay.
Right. So this Q enclosed means total Q. Right. So that's the total closed charge inside. So if you had, if I had this surface and I put plus Q here and a plus 2Q here and minus Q here, then I can guarantee the integral of E vector dot dA over the whole closed surface is going to be 2Q over epsilon naught. So I don't know what E is at any one spot here, but I do know that if I integrated E dot dA over the whole surface, I would definitely get that. And another slightly more subtle one, if I had this, and I put a charge plus Q here, it's getting too full. So that's something else, right? So if I had a closed surface like this, and I put a charge plus Q here, and now at this spot, right here, E points that way, dA points this way. So that tells you there's negative electric flux through this square, because E flux is the outward flow. And so E points that way, dA points that way. Over here, the E field at this spot from this, E points this way. dA also points that way. So there's outward electric flux here. Over here, the electric field at this spot, E points that way. dA points this way. So there's basically almost no flux through this screen square. And so you can see at some places there's negative flux, at some places positive flux, some places no flux through some of the squares. If you integrated that whole thing,
isn't it 0 too?
Yep. Right? Q enclosed over epsilon naught. In this case, Q enclosed is 0. So this whole integral, if you integrated E dot dA over that whole surface, I guarantee you get 0. Even though you don't know what E is here or here, because you don't even know how far apart anything is or the shape of this, doesn't matter. So you don't know what E is anywhere, but you do know the value of the integral. Right? So it's the same thing if you tell me you drive from, I don't know, from Albany to New York and it's 150 miles, I know that during your drive, I know this integral is, so this would be, say, I don't know, miles per second and then times seconds. I know the value of the integral is 150 miles. I know the value of the integral of V dt. I have no idea what V is at any one instant. If you ask me how fast were you going at 2:05 p.m., I don't know. But I do know the value of the integral. This is the same thing. It's a case where you know the value of the integral, but you don't know the value of E at any spot. And if this seems crazy to you, like, wow, how can it always work out to be 0? Again, go back to the water analogy. If I had this some weird screen shape there, and I had a flow, and this thing were in a river, or let's say, let's do it different. Let's suppose I had an object here spraying out, again, 1 gallon per second. So kind of spraying out in all directions. I do know that there is negative water flux through this square because dA points out and the flow, sorry, dA points that way and the flow is going in. So there's some negative flux through these squares, but then it's coming over here and there's some positive flux this way because the flow of water and dA are the same. I do know that the total flow through that closed screen, I do know it's 0. I don't know what the flow is through any one spot, but I know the total flow is 0. All right. Okay. Good. So let's do some other. Go back the first slide at some point. Yes.
Professor, sorry, I'm trying to wrap my head around it. So the flow would be 0, but there's something flowing through it though.
Yeah, hang on. Let me. So whoever wanted this, is that good? Nikita, is that good? You have it? Okay. Yeah, so that's right. That's a very good question, right? You should spend time wrapping your head around this, right? Because you look at this and you say, but the flow is not 0. How can it be 0 in this case?
Well,
sorry, go ahead.
If I may, isn't that because everything that's flowing in is flowing out?
Yes, very good answer. So, right. So it's not that you're trying to measure the absolute value of flow at each spot. Flow is a signed quantity. And so you have the flow, if you have a gallon per second spraying out here, you have negative flow through this square because it's coming in. You have positive flow through this square because it's going out. Right?
So I see why it's Q enclosed then. So because it's not enclosed, because it's leaving, then there's 0. Okay. Exactly
right. And what you notice is that here, when this spray in the water analogy, when the sprayer is outside this potato skin made of screen, the net flow through the walls is 0. And I move it closer and closer and closer, and it's still 0 net flow. As soon as it jumps over here and is inside, now the net flow is always out through all of these walls because it switched sides here. So all of a sudden now it's positive net flow. The water flux through this screen is 0. Is positive. It was 0 as soon as it's outside. Same thing happens with the electric charge. If the charge is outside, now you have some E point, in this case, E is going that way, dA is going this way. So you have negative electric flux through this little screen square. And it gets closer and closer. And as soon as it jumps the boundary, now E and dA tend to point in the same direction all the way around. And now you have net outward electric flux. And so that's encoded in Gauss's law. It's the charge enclosed. All the charge outside doesn't do anything for the electric flux. The charge that's outside, I can do this and add 100 charges all over the place out here. Won't change the net flux through this closed surface. Only the charges inside the surface matter for the net flow, the net flux. All right.
Okay, thank you.
Yeah, so Liam, it's like the difference between gross and net product, kind of. Yeah, I mean, there's it is almost an accounting thing, right? All the stuff outside, you have inward flow and outward flow, and they're going to knock each other out, no matter what shape you stretch or do with that thing. Doesn't matter. All right. Okay, so the crazy thing or the next step in Gauss's law, and again, you should, if you're shaky, you got to mull this over and over and over. The next step is that it turns out that you can sometimes use this fact sometimes to find the electric field around a charged object that's really a mess to do using Coulomb's law. Sometimes, not always. And for that, now I want you to remember that first example we did, right? Before we even talked about Gauss's law, when I said you pour 1 gallon of water onto this X, and then you drill a hole, whatever it was, 1 meter away, and then, I don't know, 1 centimeter in diameter. And I said, how much water flows over that or flows through a hole drilled here? And you said, well, what I know is that it would be the water is shared equally over it'll all flow out. And so it will be 1 centimeter over 2 pi meters. So 0.01 meters divided by 2 pi times 1 meters times 1 gallon. That's great. So just from knowing just a tiny bit of arithmetic, you found how much water flowed through there. And you chose a circle because, and a square would be wrong to choose to do this problem, because every 1 centimeter section along this circle shares equally. Now that's great for this problem, but if I said I spray in a gallon of water and not drop straight down, but I spray it in at an angle and it comes here and hits this spot and then kind of, spreads like that. Now, can you tell me how much, can you do the same thing and tell me how much water flows through this hole? No, Eric, you're shaking your head. No, why not? Can I still draw a circle?
No, because the water going in the direction you're spraying is going to be moving faster than the water going in the other direction than you're spraying as it spreads out, meaning it's not going to be an even circle.
That's right. So this whole thing here, that breaks down. You can't do that, but only if it's nice and symmetric. If it's symmetric, I have this great trick to do. And I can do that same trick for a pipe spraying out water, like in, cylindrically around it. So we're going to be able to use Gauss's law to do the same thing. And I know this first example we did on whatever it was, Thursday, but let's just do it again. So I take a charge plus Q, and I want to know so we're going to use Gauss's law. E vector dot dA vector is Q enclosed over epsilon naught. And I want to know the electric field at this point here, some point P, a distance R away from my charge. What's the electric field there? And I know you know it from Coulomb's law, but pretend you don't. And so if you didn't, you would say, oh, you know what? I don't know what the electric field is at this point, but I know that whatever it is here, it's the same value as it is here and here and here and everywhere on a sphere. So this is not a circle, this is a spherical shell that surrounds this point and centered on this charge. So I have no idea what E is here at this point, but I know it's the same, whatever its value is, it's the same everywhere on that green sphere, that green spherical shell. And so that lets me say that so I know the integral of E vector dot dA vector is Q enclosed over epsilon naught. And I know that by just, E is going to point away from the charge. So at this spot here, E points straight out and dA vector points straight out. Same over here, E points this way, dA vector points that way. And so everywhere, and this is the key point, everywhere on this thing, everywhere on that shell, E and dA point in the same direction, and E is the same value. So this integral just becomes E, the magnitude of the E vector, which is just E, magnitude of dA vector, which is dA, times cosine of the angle between them. Angle between them is nothing, and so it's times 1. Cosine of 0 is 1. Is Q enclosed over epsilon naught. Okay, now here is the critical point. E is the same everywhere on here, and so I can pull it out of the integral. In the same way that if you tell me you drive to New York City, I know V integral of V dt is 150 miles, but I have no idea what speed you were going at 2 p.m. If you then tell me that your speed was the same at all during all time slices of your drive, then I can do it. Then I just pull V out of the integral, and I just say V times the integral of dt is 150 miles. And then, that's probably, I don't know, whatever, V times 3 hours is 150 miles. And so I can then just say V is 50 miles per hour. Right? As soon as I know that V is a constant over the integral, then I know not only the integral's value, but I also know the value of V during the whole time. In the same way here, I already know the integral of E dot dA. It's equal to Q over epsilon naught. As soon as I if I can set up a surface where I know that E is the same everywhere on the surface, then I can just yank E right out of the integral. And so now I'm just left with E times the integral over the surface of dA. The total charge enclosed is Q over epsilon naught. Integral of the sum of the tiny squares summed over the whole surface is 4 pi r squared, just the surface area of the spherical shell. So that's E times 4 pi r squared is Q over epsilon naught, which then tells me, so I'm going up the page now, E is Q over 4 pi epsilon naught r squared. And 1 over 4 pi epsilon naught is K. So this is just really K Q over r squared. Okay?
Can you give me one quick second to write this down? Your hand was in the way when you were writing it.
Yep.
Okay, thank you. Appreciate it.
Real quick, how did you get the cosine?
Oh, yeah. So the cosine, I know in this case, I've chosen a sphere so that E always points straight out for a sphere, right? If you're standing here, E points that way, dA points that way. So E and dA go in the same direction. And so the angle between E and dA is 0. And so cosine of 0 is 1. So this 1 came from cosine of 0.
And why does it become 4 pi?
Oh, integral of
Integral. Okay.
surface area of the sphere, spherical shell, how much paint.
Yeah. And then in a sphere, it becomes, okay. Thank you.
All right. Other questions so far? Okay. So we did this second example too. I also want to watch time a little. This example we did, I'm going to do really, I guess I'll do this one quickly, right? You'd get the same answer if you had a spherical shell with charge Q, or let's just say it's a solid sphere. Solid sphere with charge Q evenly distributed throughout its volume. Right? Now you say, what's the total electric field at this point P here? Well, doing this with Coulomb's law would be a pain because you're going to have to find the E field here from this thing, which points that way, the E field here from this part, which points over here. And so you'll get crosswise components canceling, and you're going to have a messy integral with a lot of geometry and trig to get the E field there. But again, you can imagine what's called a Gaussian surface. So this is our Gaussian surface. So I'm just imagining a surface, just like you did with the water example, pouring water on the table. So for any surface I imagine, and this is supposed to be centered on the middle of that. So if P is a distance r away from the center of that sphere, again, what I know is that integral of E dot dA is Q enclosed over epsilon naught. Okay, so again, so whatever E is here from all these different contributions, it's the same here as there, as there, as there. And I also know it's going to point straight out. So if you're here, E points this way, dA points that way. So again, in this case, E and dA are parallel. And so this will give us the surface integral of E times dA times cosine of 0, which is 1, And the total charge enclosed in this spherical surface is Q over epsilon naught. And so this will give us the same, E is the same everywhere on that
You
surface.
said the 1 is from cosine of 0?
That's right, yeah.
I just want to write that.
Yeah. And so E comes out again because it's the same everywhere on this surface. So that's going to give me E times the surface integral of dA is Q over epsilon naught. That's again 4 pi r squared. And so same as before, you'll have E is Q over 4 pi. Sorry, this is 4 pi r squared. So you get the same thing we did before. This integral is just 4 pi r squared, so just divide. All right. Okay, questions on this? It's basically, you look at it and say, well, it's the same as the point charge, and it is in this case. So let me show you a couple of subtle things. You don't necessarily need to write this one down, but I also could make a Gaussian, rather than a sphere around this sphere, I could have made a Gaussian surface that looks like this around that blob, or sorry, around this spherical charge. So what's the integral of E vector dot dA over this red surface? If you found E at every spot here from this sphere using Coulomb's law, dotted it with dA and integrated it over the whole surface, what would you get for the integral? I claim you would get this. You'd get Q over epsilon naught. Same thing. You'd get the same value. In the same way, if I have a gallons per second sprayer here, the screen, a spherical screen, will get a gallon per second of flux through it. So will a weird shaped squash screen. Doesn't matter. They'll all get the same flux through it. So the integral of E dot dA over this weird surface will also be Q over epsilon naught. Here's the difference though. This won't help you find the electric field here. That's the critical thing you got to think about. Yes, you would know the integral, no matter what I surround this with, the value of this integral will always be that. But in some cases, if you choose your surface wisely, you'll be able to just pull E out of the integral and use it to solve for the electric field at a specific spot. Here, at the red surface, yes, the total integral is Q over epsilon naught, but I don't know how that's going to help me find the electric field at point P. Because when I go through, I'm not going to be able to pull E out of the integral because you can't guarantee for me that E is the same everywhere on this red surface. It's exactly like if I said I pour a gallon of water here and I drill a hole 1 centimeter in diameter there, and then somebody comes along and says, oh, I can find how much water passes through over that. I'm going to draw a line like this, and I know 1 gallon does pass over the red line in total. Great. That you may know that. How is that going to help you find how much water pours over this little hole drilled there? It won't. You know the integral, the total flux crossing the red line, but because you haven't chosen a line that shares the water equally, chosen a line where the flux is the same at all points along the line, you won't be able to just do that little bit of arithmetic to find the flow over that hole. Same thing here. You may know the integral of E dot dA here is Q over epsilon naught, but it's not going to do you any good to find the E field for finding the E field here. But if you choose a sphere around the sphere, then you can. All right? Okay, so mathematically, Gauss's law is probably less complicated, like less messy than Coulomb's law problems we did with continuous distributions, but it's much more subtle. Right? So it takes people a long time, including me, when I learned it takes a long time of mulling before it will hit you how it works. Yeah.
So earlier you corrected your diagram to make it a solid sphere instead of a shell. Would the answer have been different if it was a shell?
Nope, wouldn't have been. It was just I did the shell last class, and so I wanted to just change it.
Okay, thank you.
Yeah, it would have been exactly the same. Okay, so how about this? I'm going to take this thing, this solid sphere of charge, and I'm going to sort of squash it. I'm going to stomp on it a bit, and now it's going to look like this. And it still has charge Q on it. I can't draw a radius because now it's not a sphere. And again, I want to know the electric field at point P, a distance r away. What do? You cry because this can't be done with Gauss's law. Because if I draw a sphere around this, it is still true that the integral of E dot dA, if you found E from this crushed sphere at every point and dotted it with dA and integrated it around the whole sphere, you would definitely get Q over epsilon naught for that integral. Great. But that's not going to help you because now E and dA don't always point in the same direction. I don't know if you're up here because now this isn't a nice sphere. I can't guarantee that E and dA will always point the same way. Also, E is not the same value at all points on that sphere, on that shell. And so this is true, but not useful. Right? So this is still true, but it's not helpful for finding the E field at that spot. So the short answer is from this, you just can't use Gauss's law to find the electric field here. And it's one of the, the reality of Gauss's law is it's very helpful in very symmetric problems. In problems that aren't extremely symmetric, it's not of much use. It's still true, but it's not very useful. Okay, think about questions before we do a couple other examples. Okay, so we're going to do one more spherical example and then move on to a couple other geometries. Okay, so suppose I have a solid sphere. Actually, well, two more. Let's say this is a shell. All right, what's the E field here? So this thing has a radius capital R. What's the E field at that radius little r? So inside, so you have a charged hollow shell and you're standing inside. What's the electric field there? Well, what I know is always true for all points in space for all charge distributions. Integral of E dot dA over any closed surface I choose will be Q enclosed over epsilon naught. All right, so I'm going to draw this as my Gaussian surface. And the dotted just reminds you that this is just an imaginary thing we're using to solve a problem, not a physical thing. So right now, you probably don't, unless you remember it or seen it somewhere else, you don't know what the electric field is here. But you know the electric field here is the same as there and there and there because it's all, right, this is perfectly symmetric. So how could the E field there be any different than it is there? So what you know is that integral of E vector dot dA vector is charge enclosed divided by epsilon naught. What's the charge enclosed by this dotted line? All right, what's the total charge enclosed in that? So I have imagine a charged basketball, and now you make this spherical surface within the basketball, and I'm asking how much charge is inside it? 0. Yep, thank you, Scott. Right, total charge inside of this is nothing. because the charge is out here. There's no charge inside this spherical shell in there. So E dot dA is nothing. And I know that E is the same everywhere on here or out, whatever. But I know that E has got to be 0. So the electric field everywhere inside this shell, everywhere inside is 0. Okay. Now, you have to be careful. So questions on this so far? You have to be careful not to take this too far. Suppose I squash this thing a little bit, right? It is not 0 in here because you're inside a shell that has, yes, it's 0 because only the shell is charged. Yeah, this is charged. This is not anything. That's just an imaginary shape we're thinking of to help us solve the problem, said Daniel. So if I step on this and squash it a little, there's a tendency for people to want to overstate what this result is. This is not 0 just because you're inside a hollow charged shell. So now this, what used to be a basketball is now like a half deflated, right? It's now a half deflated ball. Just picture Tom Brady. This now is partly deflated, and now it's changed shape, and it still has charge Q on it. And okay, so this has charge Q on it, and now I want to know what the electric field is at point P. Still, it would be true if I drew this as my Gaussian surface. Sorry, I was using red before. I could draw, I don't know, whatever Gaussian surface I want. The integral of E vector dot surface is still 0 because there is no charge inside that surface. And so integral of E dot dA is 0, but, and this is the critical point, I can't say that E is the same everywhere on here. And I don't know how E's facing and dA's facing compare at all points on here. And so this is still true, but E is not necessarily 0 at any point on the surface, at any particular point on the surface, right? So I know the integral, but because the value is not a constant on the surface, I don't know the value at any point on the surface. Okay.
Can you go back to the first one? Can you explain why E is 0 again?
Yeah. So in this case, you know, I don't know. It'd be hard to, you have to kind of guess. You'd say, well, I don't know if E points in or out here. Let's say maybe you think, because this is a charged shell, maybe you think E points inward at P. And so then E would point inward there. Maybe you think E points inward from a charged shell like that. You know what I mean? Who was asking the question, was that?
That's me. You call me Addy.
Oh, all right. So Addy, so suppose you decide E points probably inward because this thing is a charged shell, maybe positive Q. And so then you would say, all right, at this point, E is something I don't know. dA for this closed surface points out. And so this integral, the integral of E dot dA, that's going to be E, whatever the value of E is. And because by symmetry, and since this is a shell, E is the same everywhere on this. Even though you don't know its value, you can say it's the same everywhere. And it points opposite to dA. So you would have E times dA times cosine of the angle between them. dA is out, E is in. So that's pi. So cosine would be -1. And then you'd say, well, look, E is the same thing everywhere. And so you'd pull E out of the integral, and that would leave you with E times the surface integral of dA times minus 1. And then you notice, you say, okay, the right-hand side of this whole integral has to equal 0 because the total charge enclosed by this thing is nothing. And so this equals 0, and so this equals 0, right? So this is just the right-hand side. And so therefore, and this is 4 pi times radius squared. So you have minus e times 4 pi r squared equals 0, and therefore e equals 0. Now, as soon as this shell, if you ask this for a point outside, so, well, first of all, is that okay, Addy?
Yeah, I understand it.
Right. So Stella, yeah, why it's minus 1? Because I kind of took a guess. I said, well, let's suppose the E field inside a shell, because we don't know it, right? We don't, when we're doing Gauss's law, we don't know the answer yet. I said, let's suppose our guess for the E field inside a charged shell points inward. So then E would point in, but D Gaussian surface. So dA points out, and I'm guessing E maybe, if it, I know it's non-zero, but, or sorry, I know it's 0, but if it were non-zero, maybe I would guess in, because you got this charged thing out there, and maybe it has an E field pointing in. So E and dA point the opposite direction. So E vector dot dA vector is E times dA times cosine of 180 degrees, or pi radians, and that is minus 1. Right? So you get E times dA times minus 1. And then I pulled the minus out, which doesn't ultimately matter because E is 0. Right? Is that okay, Stella? Okay. All right. So yeah, so for not symmetric shapes, it's not so easy to do. All right, let's do another case where we can do this. And this is one we did with Coulomb's law. Let's say I take a long line charge with linear charge density lambda. So this has, so lambda coulombs per meter. And I want to know the electric field at a point P that's a distance r away from the line. And this thing goes off indefinitely in both directions. Lambda coulombs, so a charged line. And you know how to do this with Gauss's law. You got to do, sorry, with Coulomb's law, kq over this distance squared as a function of position, and then you have to integrate. You know, the crosswise components cancel, verticals add, and you have to integrate from, you know, over the all the contributions of the whole line. And you get that big, messy integral. All right. So, okay. So yeah, Brady, I don't know. Things are laggy. All right, maybe I'll talk slow. I don't know. We're at the mercy of Zoom. Let me make sure it's not me.
I believe if you unshare and then reshare, it should help with it.
All right.
Just like quick.
All right, hold on.
I've had like
unshun, reshun. All right, hold on.
Yeah, on my end, your audio is just fine. It's just the video is choppy.
Oh, all right. So let me try resharing. Right, so it's the... Okay, we'll try this. All right, so how do you do this with Gauss's law? Yeah, linear charge density is lambda. Okay, so what do you do? Well, in this case, our Gaussian surface is going to be a cylinder. So I'm going to imagine basically a soup can. So I want you to imagine a soup can made of screen, including the ends. Right, so I don't want to draw all over this, but right, you've got screen there, and the curved part too. Okay, so Gauss's law, so the reason we choose this shape is I know that I don't know what the electric field is at this spot, but I know it's going to be the same everywhere on this curved part of the soup can. Even though I don't know its value, I know it's the same everywhere. And that's why I chose that shape. Is Q enclosed over epsilon naught. All right. Good. So now I have to figure out E integral. So let's do the left-hand side first. So the left-hand side of Gauss's law says we want the integral of E dot dA over this whole soup can, the ends and the curved part too. Okay, so this will be the integral of E vector dot dA over the curved part. Now remember, this part is not, there's no loop here because this is not closed now. I just want E dot dA over the curved surface plus the integral of E vector dot dA over the two ends of the soup cans, of the soup can. All right. Well, the integral of E dot dA over the curved part, you know, just from sort of physical intuition that the electric field here points straight out, right? For a long straight wire, the E field here points up. Here, the E field points straight down. Up here, it would point toward you. Down below the paper, it would point straight back. So it always points straight away from the wire. And so does dA. E and dA point exactly the same direction. Okay, so good. So this is going to be equal to, and I know that E is the same everywhere on here. So this is going to be integral over the curved part of E times cosine of 0. That shouldn't say theta, that's 0, which is 1. So this is going to be equal to, now E is the same everywhere on the curved part, so that can come out of the integral. So this will be E times the integral of dA over the curved portion times cosine of 0, which is 1. So I'll just leave that off. And so I pulled E out because I was able to choose a shape where it's the E field is the same everywhere on the curved part. Integral of dA over the whole curved part. Let's suppose this, I should have said this before. Let's suppose the size of our soup can is length L. So the surface area of the curved part is going to be, E times integral of dA over that thing is going to be 2 pi RL. Just the surface area of the curved part. Okay, so that's the integral of E dot dA for this particular shape for the around this wire for a can of length L. So questions on this part? All right, let's do E dot dA over the ends of the can. So here you got to think for a second, right? Imagine if this were a thing spraying water out, you know, perpendicular to the pipe, right? Water would be coming out that way. What's the water flux through a screen end of the soup can? Be nothing, because the water's flowing this way and the normal to the soup can is that way. So here, this is going to be equal to 0 because E is perpendicular to dA. In terms of what we've seen, the way we've been writing things, if you're standing at this spot, E points straight away from the wire. dA points this way. And in terms of flow, you're thinking there's no electric flux through this end because the flow is perpendicular to the normal. So there's no flux through the ends of the can. So the total the total integral of E dot dA is going to be that plus 0. So it's just going to be E times 2 pi RL. All right. All right, questions on this part? Okay, let's work on the right-hand side. Total charge enclosed, Q enclosed over epsilon naught. What's the total charge inside that soup can, right? So you got to now physically imagine the can comes through and chops out this section, and there's it's whatever charge is on this part of the wire. How much charge is on a wire of length L, a piece of this wire of length L, if it has linear charge density lambda? Right, so this would be lambda times L. Lambda coulombs per meter times L meters long over epsilon naught. So Q enclosed over epsilon naught is just lambda L over epsilon naught. So from Gauss's law, since integral of E dot dA is Q enclosed over epsilon naught, we can say that that equals that. E times 2 pi RL has to equal lambda L over epsilon naught. Solving for E tells us that E is equal, so the L's cancel out, gives us lambda over 2 pi epsilon naught R. And that's the same result we got before by doing that long, messy integral. Okay, so think about questions on this for a minute.
Can you just leave it for a second because it was hard to like copy down and follow? Your video is still choppy. Thank you.
Yeah. Yep, I'll just leave it for a minute.
If you're in the Monday discussion, we actually did this problem yesterday.
Oh, good. Yeah, there are a limited number of Gauss's law problems that you can actually do. And so this tends, right, spheres, lines, and we're going to do a surface in a second.
Can you talk about how you like sort of split the left-hand side with the ends and the curved?
Yeah, so what you need, so you've got this line and the electric field comes out in all directions. It comes out perpendicularly to the line. And I need to find the flux through, I used to have a can up here. So hold on. Right? Aha. So here, good. High tech. So forget about the hole in the center, right? So here's the cylinder and the line charge goes through. And so I need E dot dA integrated over this and also over these. But E is pointing straight out. So I need to integrate the surface, the flux through the whole surface. You got to imagine screen here and then screen here too. And so I split it into two parts and said, let's find the flux through the curved part. And separately, let's find the flux through the ends. And so we did them separately. So we did the curved part. And here I said, well, look, E and dA point the same direction. So E dot dA is just E times dA times cosine of 0. But for these parts, if this is the line charge, E is pointing this way, but dA for this surface points that way. And that corresponds to your physical intuition that if I had a pipe spraying water out vertically, perpendicularly to the pipe, and this thing were made of screen, there is no water flow through these ends because the water is coming out this way and these ends face that way, right? So that they would give no contribution to the flux. So does that answer your question?
Yeah.
Sort of. Or? Okay. All right. So let's do one more. So this is a problem. This is the same one I did on video, and I'm going to try to transition to having maybe just having more topical or review things on videos. Just because videos can be helpful because you can watch them at your own pace and repeat them. Oh, one thing I have to say about this problem before we go on. If you look at this, notice that our final answer, L, dropped out. And that's a good thing because it would be pretty strange if I said you have a line charge, a long line with this much charge density on it, and I want the electric field a distance r away from the line charge, and somehow the electric field here near a line of charge, if it depended on the length of an imaginary cylinder that you're thinking of, that'd be a problem if that were in the final answer. So E field here can't depend on the size of some imaginary shape that we cooked up to solve the problem. So if geometrical things about your Gaussian surface wind up in your answer, or arbitrary things that you can adjust, then you know something's gone wrong. But right, so they should cancel, and they did. Okay. So let's look at, there's a video where we found the electric field above a sheet of charge. We actually did it for a disk. And then at the end of the video example, we say, well, what if the disk is huge? What happens in the limit that the disk gets very large? So you have a big flat sheet of charge. What's the electric field here? So an infinite sheet of charge. Right, and then this will have surface charge density. Right, so this many coulombs per square meter. Right. Okay, so in this is a little confusing. You got to imagine, right? So this whole thing is uniformly charged. Oh, this is not going to fit under the camera, but I'm going to take this, and my Gaussian surface is going to plunge through here, and it's going to be a cylinder, and half the cylinder will be above, and it's going to keep going through, and it's going to come out underneath. So it's a soup can, but it's like half above, half below the surface. And so now I will so when I draw this sketch, this is what I'm trying to draw, this thing plunging halfway through, and it's above and below like that. And this is the charged surface. Okay, so this thing means this is above, comes down, hits the surface, and then sticks out below like that. You get the idea, I hope. Okay, and let's give this thing a radius of r, and we are at some height, so let's say some distance d above the surface. This is the point I want the electric field. So this has surface charge density sigma, and I want the electric field at point P, a distance d above the surface. Right. So by Gauss's law, I know integral of E dot dA is Q enclosed over. All right. Well, let's look at that. So the left-hand side, integral of E dot dA is going to be equal to the integral of E dot dA over the curved parts again, plus integral of E dot dA over the ends of the can. Now here you got to be careful. So if I just had this uniform sheet of charge, say it's positively charged, what's the direction of the E field at this spot? Just physically, what do you guess? Right, so it's infinitely big sheet of charge and a positively charged thing, and you're here above it. E field's got to point straight up because it can't point in, like if it pointed this way, you would say, well, how did you choose that way and not this way or that way? By symmetry, the E field has to point straight up. I don't know what its size is, but E field definitely points straight up. So at all spots, it points straight away from the surface, and underneath, E field would point down. Right? And I know it's the same everywhere on this end. And here, on the curved parts, E is going this way, but dA is pointing out. Again, now you're thinking if you have an infinite sheet spraying water vertically up and vertically down, there is no flux through the curved parts of the can because the flow is going that way. The normal is out like this. And so this part, the curved part, this will be 0 because E and dA are perpendicular. For the end,
I have a quick question.
Yeah.
So for the curved part, why dA doesn't have a vector sign above it?
It should. Thank you.
Okay.
Yep, it should.
Thank you.
Thanks. So E is perpendicular to dA. So for the curved parts, that integral is 0. For the ends, E is parallel to dA. So it's going to be E times dA. E is going to be the same everywhere on the end of this cylinder. And so this thing will be equal to, so I can pull it out of the integral over the ends. And so this is going to be E times pi r squared, plus there's more flux through this end, E times pi r squared. So this will be E times 2 pi r squared. So that's the total flux through E pi r squared through that, E times pi r squared through that. And so that's the total flux through the ends. So the left-hand side is going to be equal to E times 2 pi r squared times 0. So it's going to be 2 pi r squared E. For the right-hand side, I'm sorry I'm rushing a little. I want to finish this before the end of class, and then we'll have a minute or so for questions. So for the right-hand side, how much charge is inside this can? Right? It's whatever charge is on this part of the plane that's been captured in here. It's that times the charge, right? The charge density times that area. So that is going to be sigma times pi r squared. So Gauss's law tells us that these two things are equal. So 2 pi r squared E, 2 pi r squared E equals sigma times pi r squared, which tells us then that E, so the pi r squareds cancel. So E is, shoot, I screwed up, sorry. Right, it's right-hand side is the charge enclosed divided by epsilon naught. So I forgot to carry the epsilon naught. So 2 pi r squared E is sigma pi r squared over epsilon naught. So E is so cancel the pi r squareds, and E is equal to sigma over 2 epsilon naught. Which is the same when you watch that video example, the same answer we got from Coulomb's law. But that one was trickier. We had to do a ring integral and then integrate over rings to get a disk, and then take the limit as the radius went to infinity, and we wound up with this as our answer. Right? So that's the electric field above. And again, the size of the electric field does not depend on the radius of an imaginary circle, or the radius of an imaginary cylinder that we cooked up to solve the problem. Right? All right, so questions on this? Okay, I'll try to set up a, I'll set for people who said they could actually meet in person for an occasional office hour. I don't know how often I'll do it, but I might just do it sometimes. I'll send out a doodle poll. Obviously, don't answer the doodle poll of what day works best for you if you can't or don't want to do that. But for those who would show up, just answer the doodle poll when it comes around. All right. I'll try to pick a time of the week that works for as many of you as me and as many of you as possible. So, all right. So quick questions on this before we sign off. Okay. So mull over Gauss's law over and over and over. And when you're doing these with flux, try to think back to that first water example of flow over a circle with water on a table. That analogy helps some people. So, and other than that, I will see you on. I'll see you on Thursday. I'm sorry there are no office hours today.
Professor, I have one extra question that has nothing to do with this. About the quiz. Yeah. I was wondering, would it be possible for you to post the solution for the quiz like you do for the homeworks?
I think, so quizzes are up to your TAs. I don't, they're making, I think at least, I believe they're generally going to make a different quiz for every single section, which is like 8 or 10 sections. And so I don't know that they can post 10 full detailed solutions every week.
Okay. I didn't know they were different. Okay.
Yeah. But what they are, but you should absolutely ask them if you don't get it right, ask them how to do it in class. And I'm sure they'll go over it in class if you ask them. Right. Okay, they'll probably say any questions on the quiz, or if they don't, just ask and they'll show you. Or you can also come to office hours and ask how to do it there too. Or they might post like 1 or 2. So I don't know what they're planning, or maybe just some simple sketch solutions, but I think they can't do 10 a week.
Sir, could you explain about RHS again?
The which?
RHS, the last one.
Yeah, the right-hand side. So so if this cylinder punches down through the plane, right? So this thing has a surface charge density sigma, and I take a can of radius r and it punches down through here. How much charge is enclosed inside the can? Well, it would be whatever charge is on this part of the plane, right?
Yes.
Because this is the part that winds up inside the can. Okay, so how much charge is on a circle of radius r out of this plane?
So that symbol is similar with lambda as before, right?
Yeah, so be careful. Lambda is how many coulombs there are. Like if I have a line, we typically use the letter lambda for how many coulombs per meter there are on a line. Sigma it's custom to use for surface charge density. How many coulombs there are for every square meter of this thing.
Oh, okay. Got it. Thank you, sir.
It's the same as mass. In fact, if you look at a package of plain copy paper, you'll see somewhere on the side of it, it'll say how many grams per square centimeter your paper is. Right? It's telling you how many grams it would be for every 1 square centimeter you cut out of it. So this is the same. If I smeared it with charge, you say, well, how much charge? And I'd say, there's 0.1 coulombs for every square meter on here. So then I say, all right, how much charge is on that circle? It'd be sigma times pi r squared. Yeah. Okay, good.
Bye.
All right, bye. And if you're just showing up to 3:50, I'll be back in like 5 minutes. Lie down. I have to lie on the floor for 5 minutes between class.
Take your time.
Yeah.